In this lecture, we prove a theorem regarding how tangents and radii of circles are related. Let C sub 1 be a circle centered at O. Suppose that we have a line L, that intersects the circle, then with segment OT being a radius of the circle, L is perpendicular to segment OT if and only if L is tangent to the circle. Because the theorem is an if and only if statement, we have to prove two statements. First, we prove that if L is perpendicular to OT, then L should be tangent to the circle. Then we prove the reverse direction, or the converse of the first statement. That is, if L is tangent to the circle, then L should be perpendicular to the radius. So let's take on the proof of the first statement. We assume that line L and the radius OT are perpendicular to each other at the point T. We choose an arbitrary point A on line L with one condition, that A be a different point from point T. We will show that the distance of the point A to the center of the circle is greater than the radius. That is, all the points of L besides T are outside the circle, so that L intersects the circle at only one point. We take advantage of the fact that triangle OTA is a right triangle. And because it is a right triangle, the longest side will be the hypotenuse, which is segment OA. So segment OA is longer than segment OT, which happens to be the radius of C sub 1. So that indeed the distance between A and O is greater than the radius OT, so that A is outside the circle. Hence, the only point of intersection between L and the circle is the point T, and therefore L is tangent to the circle. We now prove the converse statement. We prove that if L is tangent to the circle, then L must be perpendicular to the radius OT. We use proof by contradiction to achieve this. We begin by assuming the opposite of the conclusion. That is, we assume that L is not perpendicular to OT. There are two angles that we can consider. Angle A to the left of radius OT, and angle B to the right of the radius. Because we are assuming that line L is not perpendicular to segment OT, either angle A or angle B is less than 90 degrees. Without loss of generality, let us say that angle B is the one that's smaller than a right angle. Therefore, 90 degrees minus B is positive. We should be able to construct such an angle whose measure is 90 degrees minus B, and which we call angle C. We construct this angle with vertex O, with side OT, and on the same side of OT as angle B. Let the other side of angle C intersect L at the point A, and so angle C is the same as angle TOA. And keep in mind that we are constructing angle C so that its measure is the same as 90 degrees minus B. So B and C are complementary, so that B plus C is equal to 90 degrees. We will also consider angle OAT, which we call angle D. So now we have three angles B, C, and D, which are the angles of triangle OAT. And so B plus C plus D is equal to 180 degrees. But we constructed angle C so that B plus C is equal to 90 degrees. So that we can subtract B plus C from the left side of this equation and subtract 90 degrees from the right side and still maintain equality. So that D must be equal to 90 degrees.
And so triangle OAT is a right triangle
with angle D as the right angle. And since OT is opposite the right angle, OT must be the hypotenuse, and so has to be greater than the other two sides. In particular, OT has to be greater than OA. So that A must be inside the circle, and so L cannot be tangent to the circle because it will have a second point of intersection with the circle. And so we have reached a contradiction. Therefore, the assumption that we made that L is not perpendicular to OT has to be false. And therefore, L has to be perpendicular to OT.